Sound is also periodic. So sound is a series of waves that travel through the air of high pressure, low pressure. And you can use the math of sinusoidal curves and cosine curves and all of these types of curves that we will look at to analyze sound at a high level. So if people are interested in music production, sound engineering, these types of mathematics are very much at the heart of that, and what like a modern day sound processor or synthesizer would be doing is based on this type of math. Hi everyone, thanks so much for showing up for your learning today. I remain as always Mr. Jennings, your humble math servant, and today we are getting an introduction to periodic functions. So we know that periodic functions are functions, so they all pass vertical line test, we're going to see that, that repeat themselves in a pattern or cycle. Just like walking, or your candy consumption, or your bladder filling up and then emptying, and then filling up again and then emptying. Okay? They repeat. Specifically, they repeat their y values over a series of x values. The x values are going to give you your periods, and you can stack them next to one another and see the repetitions. And the y values is the go up and go down. Okay, so let's take a look here at the moon. The moon is a highly periodic orb that floats about the Earth in its rotations. And we notice that at certain times of the month, you can see the whole darn thing. The whole darn thing is lit up. That's called a full moon. And we got another full moon there, and another full moon. Wow, almost one a month. And then we have like these times where it goes through 50% visible, and those are called quarter moons. These are called quarter moons, but we can only see half of them. It's counterintuitive. And then what's it called when you can't see any of the moon? What did you say?
I said no moon.
No moon? If I give you credit for having an accent, then you're correct. What's it called when you can't see the moon? It's dark.
Daytime.
The phases of the moon? Really? No one has? Sam was joking, but he's almost right. He said no moon, but it's not no moon, it's new moon. The new moon. The new moon is when it's like new. It's going to start again. It's blank. It's dark. That's called a new moon. Okay, so continue the graph and sketch one more cycle on this function. Okay, so let's do that. All right, so here's something that I would want to do that. I'm going to get out my pencil. So I got a pencil here, and I'm going to extend 100%. So you're going to extend 0%, and you're going to extend 50% here. Do this. Follow along with the activity, everybody. Okay. Maybe I extend 25%. Maybe I don't like this going by 10% business. I just want to go by like 25%. So I extend 75% here. All right, and then I got those. It's beautiful. And now I go over here 90. And then I go 100. And I space them roughly where I want them. And I 120, 130. Okay? Now, I'm going to go ahead and get out. I'm going to be super confident. And I'm going to be like, how are we going to extend this whole graph? Like, how are we going to do that with some like degree of accuracy? What would we want to do? I have an idea, Mr. Jennings. My idea, I use this to speed us up. My idea is that we figure out how often we're going through this repetition, this period. And then we just kind of map out all of those spots where we hit the maximums and minimums again. How about we do that? It's a great idea, Comfy Cat. All right, Comfy Cat, let's go. So here, I notice we're there at 30, and we're there just shy of 60. What's the period for this function? How many days does it take a moon to go from new moon to new moon? Are you sure about that?
124. 365 days.
To go through one cycle of the moon.
30. 25.
You don't know. It's up in the sky every day for you to see. Yeah.
30. 12.
It's about 28 days. 28 days.
Well, I was talking
Yeah.
about the graph.
Yeah. So notice we're just, it looks like 30, but we're just a little bit ahead of 0 there. We're right on 30, and we're just a little bit behind 60. It's 28 days. It's 28 days for the period of the moon. Let's just verify that, because I'm doing that based on like, about 27.32 days. So I said 28, so I'm the closest. Everyone else said 30, except for those who said things like 1 year, which was very interesting. Okay, so let's go here from 60. We're going to go just shy of 90 there. Boop. And then we're going to go from 90, a fair bit shy of 120. And that should do us for a decent degree of accuracy. And if it seems like I'm trolling you, I do so with math love. Okay, so here we go. From 70, we're going to go just a little, this is a little bit ahead of 70. So we're going to go a little bit ahead of 100, but not quite so far ahead of 100. So we're about there. And then from 100, just about to 130, like about there, okay? So just put on your maxes and mins, and then we're going to join this with a smooth curve, okay? Whee, beautiful curve. Come down here, try and turn going into that point. Don't take the corner like a young driver would take a corner. Take a corner like you know, you're gonna go through like Tokyo Drift or something like that. Did I become more passive-aggressive today? I started thinking about it. I started reflecting on my passive-aggressiveness, and I feel that I'm now seizing more opportunities to rib you. Okay, so there we go. That is our extension of this graph. I did more than one cycle, but that's fine. Okay, what is the period? We talked about that. It's actually 27.3 something days. Okay, it's weird that our months are like 30 and 31 days long, and they're based on the cycle of the moon. But actually, if you did 28 days, you'd be far closer. And you would have 13 months a year plus 1 day. You would have 12 months of 28 days and 1 month of 29 days, except in a leap year. You'd have 2 months of 29 days. I don't know why I'd have to look at that, why we do that. Okay, what's the domain and range of the function? You all let me know if you need me, if you would benefit from having your attention brought back by the bell. I should do the bell? Okay. We'll invest some time in the bell here. Student attention is also periodic. It's like at a maximum as I ring the bell, and then it starts to go down, and then I ring the bell again, and it starts to go down. Okay. What's the domain and range of this function? Which one's domain, which one's range? Is that an idea, or is that a stretch?
I had an idea, but
Jude has an idea.
The range is x is greater than or equal to 0, and then x is equal to or less than 100.
So x is greater than or equal to 0. We've also got like here, this one says days of the year. So this one could be like x is 0 to 365. Oops, less than or equal to 365. Or we could just say, you can run that to infinity. And you're still going to see the moon become visible and go away, become visible and go away. But then you said something about the range, the y values. What did you say, Jude?
X is greater than or equal to 0, x is less than or equal to 100 for range.
Who thinks we need a seating plan? Oh, prove to me that we don't. Okay, sorry? For the range, x is greater than or equal to 0, x is less than or equal to 100. Yeah. So this one we would say y here if we're talking about the range, because that's referring to the possible y values. So you see we can go as high as 100% and as low as 0% in this function. The moon goes completely away some days, that's a new moon, and it's totally visible other times, that's a full moon. Okay, and it's everywhere in between, all the different things. So there you go. Okay, maximum and minimum values. All right, I'll do that. It's 0% all the way to 100%. And so then where's the horizontal axis for this function? Like if I were to put an axis between, it's kind of rotationally symmetrical around the horizontal axis, but it's not exactly symmetrical. Like if I flip it, it's a different function. Yeah, but yeah, if I go between the maximum and minimums, that's the average of 50% and 0%. That's 50, and then the amplitude is also 50%. Okay, it goes up and down by 50%. Sorry? In this particular function, yes, but not in children candy consumption. There we found it was 110 grams per day. It's you take the average of the maximum and minimum. So here is our horizontal axis here, right? Horizontal axis, and I can write it this way. Y is equal to 50%. That's the equation of the horizontal axis. But then if I want to show you the amplitude, I might show it this way. Here is plus 50%, right? That's the amplitude. Or I go down from the horizontal axis. I want you to make these notes on your sheet as well. Point out to yourself, here is where I see the amplitude, and then here is where I see the horizontal axis. Amplitude is distance above and below the axis. The axis is that line that goes between the maximum and minimum values. Okay? All right. So here's an example for you to think about. I pause video, you think about it, pair, so talk about it with your classmates, and then we'll pick that up. Okay, let's discuss. So let's take a look at these examples. Which one of these feel periodic to you? I'll give you a hint. 2 of them are periodic and 1 of them is not like the others. Katie Bass. The first one and the third one are indeed periodic. 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 Good. But why? Why are they periodic and the other one isn't? Joel, you got an idea? No? Taylor? That's a good way to think about it. All of that, like, there is a pattern in the second one, but it doesn't happen inside the same range. We don't have the same pattern of y values repeating over and over and over again. Yeah. So this one here, we have a maximum at 4 and a minimum at 0, and it just repeats over and over. Maximum at 4, minimum at 0. And this one, I mean, this is a local maximum, but that one is clearly bigger. It's going up, right? This one here, again, maximum at 3, minimum at -1. Maximum at 3, minimum at -1. What's the period for this one? I would find the distance between maximums here. The distance between minimums, if I go from there to there, it's okay, but not there to there. That's different. That's not the whole pattern. So our period here is this distance. What is that? 8. 8 is correct. Yeah, so the period equals 8. And the amplitude, well, to find the amplitude, I like to find the horizontal axis first. But here's the point where you're going to want to copy down some cool little formulas. I have my max is 4, and my minimum is 0 in this case. To find the horizontal axis, I do max plus min divided by 2. In this case, that's 4 plus 0 divided by 2. That is the number 2. My horizontal axis is at 2 here. if I want to find amplitude, here is my little mini formula. Maximum minus minimum over 2. Half the distance between the maximum and the minimum. So in this case, it's 4 minus 0 over 2. It is again 2. Okay? So there is my horizontal axis. It's y equals 2. And then my amplitude is here, minus 2, or here plus 2. I liked it better when that was in orange, so I'm going to do that again. I'm just going to show the amplitude here. Minus 2 or plus 2 to go up and down from the horizontal axis. And here are my mini formulas. These are things that can score you points on tests and help you make quick work of homework things. So copy down those little mini formulas. So here our maximum is 3. And our minimum is minus 1. So what's the average of those two numbers? Is it? Is it? No, you're going in the wrong direction. No, you weren't right ever yet. 1 indeed is correct. 3 plus negative 1 is 2. 2 divided by 2 is 1. But you can also visually see it here. Okay? You can look at it this way. Here is my horizontal axis at 1. Notice how that kind of cuts the function in half. And I go up there 2, that's plus 2, that's my amplitude. And down there 2, minus 2, that's my amplitude. Minus 2 or plus 2. And this is y equals 1 is my horizontal axis. Let's try it with some of our formulas. For max plus min, I thought I changed that to black. There. Max plus min over 2 is 3 plus minus 1 over 2. That is indeed the number 1. Okay? Max minus min, okay? That's 3 minus minus 1. So if you just trust the formulas and get your signs right, it works. 3 minus minus 1 is 4. That's the number 2. 4 divided by 2 is 2. So that's where you see your maximum and minimum there. Now, one thing that I've heard people talking about a lot at this time of year is, wow, I can't believe it's still light out. The peer pressure will let them know that their behavior is not appropriate at this time. So one thing that I've noticed at this time of year is people are really excited and surprised at how long the day is getting. And they're saying things at like 8:20 at night. Wow, the sun's still up. And then they're saying things like, I woke up this morning and I thought I was late for school, but it turns out it was still 6:30 because it's so light. Because just like riding on a Ferris wheel, we are riding on a big wheel called the Earth, and it spins around the sun and exhibits periodic behavior as well, just like that wheel going around. So what I would like you to do is here I have approximate. Very nice to work with numbers about how long the day is at different times in the year. I have here a graph that goes to 12 months. Rotate your page 90 degrees, and you can put this data on there. One question to start. Where is something like 9:30 on this axis? What does that mean, 9:30? If you had to do that if you did that as a decimal, what would that be? 9.30? Yeah? Everyone happy with that?
No.
No? What is it? It would absolutely be 9.5. What would 15.15 there be? This is 15.25. That's 15 hours and a quarter. So convert them to decimals. If you're not sure how to convert a number of minutes to a decimal, you do 45 over 60 and find out what it is. So let's do that on our calculator. 45, yeah, I know what it is, but I'm showing people. 45 divided by 60 is, oh my goodness, 75 cents, 3/4. There you go. So give this exercise a try. I will come around to see your beautiful periodic graphs, and then we will bring this home. Okay, do people have something that looks something like that? Yeah. So we have here summer solstice. What does that mean, the summer solstice?
When it's
Yeah.
when the sun is up for the longest.
The longest day of the year. When the sun is up for the longest, that's your summer solstice. What day does that typically fall around? 21st of June, yeah. And then the winter solstice is very close to Christmas, December 21st or so. Okay, sometimes it's the 20th, sometimes it's the 19th or 22nd, but it's usually the 21st. And then we have the equinoxes. We're already past the vernal equinox, March 21st, where the day is half and half. So if we go through here and note, here's our axis, right? It's around 12 hours. Average of 12 hours of daylight per day. Huh? Oh, sorry? Yeah, I just go through, I look at the number and then I put it on. And then I look at the number and I put it on. Wilson? Yeah. So this is our horizontal axis at about 12 hours. And here's our amplitude. That's plus about, well, what is our maximum one? It's here, 1530. So that's 3.5 hours. An extra 3.5 hours of daylight there. And then we lose about 3.5 hours of daylight there. I think in our graph we lose a little bit less than that here. That's only losing 3.25. But these are approximate numbers that have been rounded anyway. So maybe it's in between 0.25 and 0.5. Okay? So it's about there. There's our amplitude. The period for this whole thing is 1 year. This pattern will repeat year after year after year. You could also say 12 months or 365 days, or if you know rent, 82,642 minutes or whatever it is. Okay. So, practice in your textbook and notice in your life periodic things that happen all around you. Bye for now, everyone.